Welcome viewers. In this lecture, we are going to explore one of the most subtle and intriguing behaviors in digital signal processing, the Gibbs phenomenon. You will learn what it is, why it matters, and how mathematical techniques like Fejér summation help mitigate its pesky overshoot. By the end, you will have a thorough grasp of what's happening behind the scenes when we approximate signals using truncated Fourier series, as well as a practical method to reduce these unwanted oscillations. In digital signal processing, we commonly represent complex periodic signals as a sum of simpler components, sinusoids of different frequencies. This is the essence of a Fourier series. By summing enough sinusoidal terms, we attempt to reconstruct our original signal. This approach is powerful and underpins a wide range of technologies, from image compression techniques to audio synthesis. But there's a catch. When the original signal contains a sharp discontinuity, like a square wave's sudden jump from -1 to +1, a truncated Fourier series approximation doesn't neatly snap into place at that jump. Instead, it overshoots and then oscillates around the discontinuity. Even as we add more and more Fourier terms, the magnitude of that overshoot never fully disappears. It's a persistent trait known as the Gibbs phenomenon. The Gibbs phenomenon was first recognized in the context of Fourier series. Suppose you are approximating a square wave. With only a few terms, the approximation is rough, but as you add more terms, the waveform appears smoother and more accurate. However, near the edges, where the wave abruptly changes value, you'll notice this distinctive ringing, little ripples that overshoot by about 9% of the jump size. That's the Gibbs overshoot. It does not shrink to zero, no matter how many terms we add. This phenomenon reminds us that a finite sum of sinusoids cannot perfectly replicate a sharp transition. Instead, it creates a sort of ringing artifact right at those discontinuities. Here, you see a standard demonstration of the Gibbs phenomenon. We start with a square wave and approximate it using 5, then 15, then 50 Fourier terms. Notice how the overshoot persists. As MIT open courseware materials indicate, this persistent overshoot is not a computational glitch. It's mathematically inherent in the partial sums of the Fourier series. At the heart of this lies the Dirichlet kernel, which is used to construct Fourier partial sums. The Dirichlet kernel tends to have large values at certain points, causing a high-frequency ringing near discontinuities. The kernel is effectively a filter that tries to reconstruct the original function from its Fourier coefficients. But because it does not dampen the contribution of the higher frequency terms well, it ends up causing spikes near sharp transitions. To put it simply, the Gibbs phenomenon emerges from how the partial sums behave around discontinuities, influenced by the properties of the Dirichlet kernel. As the Purdue University material on FFT and Gibbs phenomenon notes, the overshoot is here to stay if we rely solely on standard partial sums. You can visualize the Dirichlet kernel as having large oscillations that never quite die down fast enough to avoid overshoot. So how do we fix or at least mitigate the Gibbs phenomenon? One initial approach in DSP is to use windowing functions. By applying a window, like a Hamming or Hanning window, to the Fourier coefficients, we effectively reduce the impact of high-frequency components that contribute to the ringing. Windowing can soften the edges of the approximation, but it doesn't completely eliminate the overshoot. It just makes it less pronounced. Think of windowing as applying a gentle blur at the edges. A more elegant solution comes from a technique known as Fejér summation, described thoroughly in resources from Graz University and in various functional analysis texts from MIT. Fejér summation involves taking the arithmetic mean of the first and partial sums of the Fourier series, rather than just using the nth partial sum. By doing this, we replace the Dirichlet kernel with a related kernel called the Fejér kernel, which is essentially a smoothed version of the Dirichlet kernel. The Fejér kernel acts like a built-in averaging mechanism, effectively dampening those troublesome high-frequency oscillations. The result is a series approximation that converges uniformly for continuous periodic functions and significantly reduces the overshoot seen with the with the Dirichlet kernel alone. It won't produce a perfect edge on a discontinuous function, but it does reduce the amplitude of the overshoot, making the approximation visually and numerically more pleasing. As the MIT OCW functional analysis lectures emphasize, Fejér's theorem guarantees that the Fejér means of the Fourier series converge uniformly to the original function if it is continuous. While for discontinuous functions the convergence is still pointwise, the Gibbs type oscillations are diminished. To recap, we have three scenarios. Plain, truncated Fourier series Dirichlet kernel produces the Gibbs phenomenon, persistent overshoot at discontinuities. Windowing reduces the severity of the overshoot, but does not fundamentally alter its existence. Fejér summation, C0 means, averages partial sums, replacing the Dirichlet kernel with the Fejér kernel, and significantly curbs the oscillations. While Fejér summation doesn't eliminate all issues in the sense of producing a perfect step transition, no finite sum of sinusoids can truly jump instantly. It offers a more controlled, smoother approximation. Practically, this is very valuable in DSP tasks, where sharp transitions cause unwanted ringing in filters or reconstructed signals. In real-world signal processing, we often deal with signals that have abrupt changes, edges in images, transitions in communication signals, or sharp attacks in audio signals. The Gibbs phenomenon can introduce artifacts like ringing along sharp midge edges or tonal artifacts in audio. By adopting approaches like Fejér summation, DSP engineers can reduce these artifacts, enhancing the quality of compression, transmission, and reconstruction techniques. This balancing act between theoretical purity and practical approximation is a hallmark of engineering. Understanding how to mitigate phenomena like Gibbs overshoot can lead to sharper images, clearer audio, and more reliable communications. You now have a working knowledge of the Gibbs phenomenon, what it is, why it appears, and how to address it. We started with a classic Fourier series approximation of a square wave, noted the persistent overshoot, and explored mathematical and practical techniques to reduce it, particularly Fejér summation. Keep this knowledge in mind as you progress in DSP. When you see undesired oscillations in your filtered signals or compressed images, remember that clever averaging kernels and summation techniques can help. With this, you've learned a valuable lesson in both the mathematics and the engineering of signal processing.